Hello everyone, this is the 1.3 section of notes, which I tend to think is pretty friendly as far as this class goes. It doesn't require a table, and you learn some convenient ways that let you take limits much more quickly than in the past. So as we discussed in the last set of notes, the limit doesn't care about or depend upon what's actually happening at the particular x value in question. But for functions that are continuous at that x value, the limit and the value of the function should be the same, and we can just use substitution to solve limits quickly. Here are some basic rules of this fact. If you have a constant function, the limit as x approaches any value of that constant function is that constant. If you have a linear function, the limit as x approaches the value of, say, x is just c, so you can just plug in c. And even if you have a linear function raised to a power, it continues to be true that you can raise that number to the power. So let's find the following limits. The limit as x approaches 2 of 3. 3 is a constant, so the limit as x approaches 2 of the function 3 is 3. This is like an example 1. The limit as x approaches -4 of the function x, well, again, we can just plug it in because it's linear. So the limit as x approaches -4 of x is, you'd replace x with -4. And the limit as x approaches 2 of the function x squared means we just plug in 2 and 2 squared, which is 4. So that is a lot faster than the way we did limits, either with a table or with the graphs. And the truth is, when you have continuous functions, the limits behave very nicely, much like plugging in the functions. And it will be faster. Now, because of this arithmetic and some of the properties of how math works in our numerical system, we have some other rules. So if you have two functions, one has a limit that's one constant, and the other one has a limit that's a different constant. If you multiply a function by a constant, for example, if instead of limit as x equals -4 of x, we had 3x, you would just take -4 and multiply it by that same constant 3 to get -12. If you're adding the limits of two functions, it's the same as finding the limits of the two functions and adding those limits, whether you're adding the function inside the limit or outside. Sometimes this is read as the sum of the limits is the limits of the sum, or the limits of the sum is the sum of the limits. Similarly, for the product, you can take the limits of the two functions separately and then multiply them if those two functions are multiplied together. Same with quotients, but you can't divide by 0. And raising things to powers, which will include roots, because roots are, of course, just fractional exponents that can be represented as powers. So we can do some more examples. The limit as x approaches 2 of 4x squared plus 3. Again, it doesn't really matter what's going on. This is a continuous function, at least at that x value in particular. So 4x squared plus 3 is 4 times 2 squared plus 3. The limit as x approaches 2. We can just plug in. So this is 4 times 4 plus 3, which is 16 plus 3, which is 19. So that means the limit as x approaches 2 of 4x squared plus 3 is equal to 19. So with a fractional exponent, again, we can just plug in. As a reminder, when it says the limit as x approaches 4 of 5x to the 1/2 minus 2, this is them saying, remember, 5x to the 1/2 is the square root of x. So this is really 5 times 4 to the 1/2 minus 2. 4 to the 1/2, the square root of 4 is 2. So it's 5 times 2 minus 2, which is 10 minus 2, which is 8. So it's the limit as x approaches 4 of 5 times x to the 1/2 minus 2 is 8. And the last one is an example of the limit of a quotient is going to be the quotient of the limits. So I will take these two limits separately. The limit as x approaches -4, 2x minus 1. the limit as x approaches -4 of x squared plus 5. And again, we know for both of these, we can just plug in. When I plug in -4 here, I get 2 times -4 minus 1, which is -8 minus 1, or -9. When I plug in -4 here, I get 16 plus 5, which is 21. That means the limit as x approaches -4 of 2x minus 1 over x squared plus 5 is -9 21sts. If you can reduce, go ahead and reduce. So I believe this should be -3/7. Now, in addition to working for some of those situations, it also works for continuous portions of radical equations, because it's really only division, composite functions, roots, and as we discussed, roots are fractional exponents, and even trig functions as well. So find the following limits. The limit as x approaches 1 of x squared plus x plus 2 over x plus 1. I noticed that this is a rational and it's not defined at -1, but it is defined at 1, so that means it's not a problem to plug in because it will not cause us to divide by 0 or create indeterminate form. So I can just plug in 1. I'm going to use a little shorthand notation. I should put f of x here, just say the function is going. So this is 1 squared plus 1 plus 2 over 1 plus 1. That's 1 plus 1 plus 2, which is 4 over 2. 4 divided by 2 is 2. So we can say the limit as x approaches 1 of x squared plus x plus 2 over x plus 1 is equal to 2. Now, one thing that's important when you're dealing with trig functions is that you remember the values of your trig functions. So yes, all we have to do here is plug in 0 for tangent, but we have to remember what tangent of 0 is. So what is the tangent of 0? It is 0. Remember, it's sine over cosine, for example, and sine is 0, and if the numerator of your fraction is 0, the whole thing will be 0, so long as your denominator is not 0, but cosine of 0 is 1. So tangent of 0 is 0, which just means the limit as x approaches 0 of tangent x is 0. And this last one on this page is kind of a hybrid. It's the limit as x approaches pi of x times cosine of x. So here is an example of a product, two things multiplied together. So again, I can instead take the two limits separately and then ultimately multiply them together. So what is the limit as x approaches pi of x? Well, we just plug in and we get pi. What happens when we do this for cosine x? Well, it's the cosine of pi, and the cosine of pi is -1. That means the limit as x approaches pi of x times cosine x is the product of these two limits separately, which is pi times -1, which is -pi. So like I said, these are relatively easy rules to follow and relatively convenient, because in the last set of notes, which is about 3 videos, we could do all of about 5 or 6 limits in 30 minutes by doing the chart and plugging things in. And in this one, we already did about 10 and under 10 minutes, so we've obviously saved a lot of time. But as you'll note, sometimes plugging in is not going to work because we'll divide by 0 or maybe have 0 over 0. So in the next video, we will learn some algebraic techniques which can help us get it to a point where we can plug in.